Have you ever pondered the origins of our vast universe? It's a question that has tickled the human intellect since time immemorial. Throughout the ages, people have spun countless tales and theories trying to decode the mystery of our cosmic roots. From ancient civilizations invoking divine architects to philosophers speculating about infinite cosmos, the quest for answers has been relentless. In the modern era, science has taken up the torch, shining a light into the dark abyss of the unknown. Enter the Big Bang Theory, the cornerstone of our understanding of the universe's birth. It's the most widely accepted scientific explanation that we have, a testament to our species' insatiable curiosity and our unyielding determination to unravel the secrets of the cosmos. As we stand on the precipice of knowledge, gazing into the heart of our universe, we are led to ask, so, what exactly is this Big Bang Theory all about? The Big Bang Theory, despite its complex nature, can be simplified. Imagine the entire universe, all the galaxies, stars, and matter, compacted into a single point of infinite density and temperature, smaller than the head of a pin. This is what we call a singularity. Around 13.8 billion years ago, this singularity began to expand rapidly in an event we now refer to as the Big Bang. In the blink of an eye, the universe expanded faster than the speed of light. Don't scratch your head just yet. This doesn't violate Einstein's theory of relativity because it was not matter, but the fabric of space itself that expanded. As the universe expanded, it cooled down, allowing particles to form. These particles eventually coalesced to create atoms, stars, galaxies, and all the structures we see in the universe today. From a hot, dense point to a vast, cool cosmos, our universe has come a long way. Now you might be wondering, how do we know all this? What's the evidence supporting the Big Bang Theory? First, we have the cosmic microwave background radiation. This is a faint glow of light that fills the universe, the afterglow of the Big Bang. This radiation is remarkably uniform, showing that the universe was once in a hot, dense state. Second, we observe the redshift of distant galaxies. As galaxies move away from us, the light they emit shifts towards the red end of the spectrum. This redshift indicates that the universe is expanding, just as the Big Bang Theory predicts. And finally, the abundance of light elements. The Big Bang Theory accurately predicts the amounts of hydrogen, helium, and lithium in the universe, lending further credence to the theory. So, that's the Big Bang in a nutshell. But what does quantum mechanics have to do with it? Well, stay tuned to find out. Quantum mechanics, another complex yet fascinating concept, plays a significant role in our understanding of the universe. At its core, quantum mechanics is the study of particles at the smallest scales imaginable. The atoms, the electrons, the quarks and leptons, the truly microscopic building blocks of everything we see around us. Let's start with the principle of uncertainty. Formulated by Werner Heisenberg, it states that we cannot simultaneously know the exact position and momentum of a particle. The more precisely one quantity is known, the less precisely the other can be known. It's not just a limitation of our measuring tools, but a fundamental aspect of nature itself. Then we have the wave-particle duality. Every particle can exhibit properties of both particles and waves. Sounds strange, right? But it's true. Light, for instance, can behave like a stream of particles known as photons and also like a wave, interfering and diffracting just like water ripples. Let's not forget about superposition. This principle states that a particle can exist in all its theoretically possible states at once. But when we try to measure it, we find the particle in only one particular state. Yes, it's as mind-boggling as it sounds. Now, how does all this quantum weirdness relate to the Big Bang? Enter quantum fluctuations. These are temporary changes in energy that occur in empty space, resulting from the uncertainty principle. Some theorists suggest that our universe itself could be the result of such a fluctuation. A tiny random quantum event might have triggered the Big Bang, leading to the creation of our vast universe. So, quantum mechanics could potentially explain how the Big Bang happened. But how does this all tie together? We'll delve deeper into that in our next segment. Stay curious as we continue to unravel the mysteries of our universe's origin story. This is where the inflation theory enters the stage. Now imagine a cosmic opera where the Big Bang Theory and quantum mechanics are the lead characters. Their performance together gives life to the inflation theory. This theory provides a bridge between the realms of the incredibly large, governed by the Big Bang Theory, and the incredibly small, ruled by quantum mechanics. In the first act, we have the Big Bang, the explosion that created our universe. But there's a plot twist. Instead of a slow, gradual expansion, the universe inflated at an astonishingly rapid rate. Picture a balloon, but instead of taking several breaths to fill it, imagine it expanding to the size of a beach ball in less than a blink of an eye. That's the kind of speed we're talking about with the inflation theory. Enter quantum mechanics in the second act. According to its principles, tiny fluctuations occur all the time, even in empty space. Now remember the rapid inflation we just talked about? Picture these quantum fluctuations happening during that time. They would be stretched out by the inflation, magnifying these minute disturbances onto a cosmic scale. This leads us to a fascinating idea. The large-scale structure of the universe that we see today, the galaxies, the clusters of galaxies, even the vast cosmic voids, could all be the result of these quantum fluctuations magnified by inflation. It's like looking at a photograph that's been blown up so much that the grainy dots of the original picture have become large blobs of color. So, what does this mean for our understanding of the universe? Well, the inflation theory adds a new layer of complexity to our cosmic story. It provides a possible explanation for why the universe appears to be the same in all directions and why it's flat, two observations that have puzzled scientists for decades. But most importantly, it introduces a fascinating connection between the worlds of the very large and the very small, tying together the Big Bang theory and quantum mechanics in a cosmic dance. So, could quantum mechanics and the Big Bang theory together answer our big question about the origin of the universe? Weaving together the threads of the Big Bang theory, quantum mechanics, and the inflation theory, we can begin to unravel the universe's origin story. Our journey starts with the Big Bang, a monumental explosion that set the stage for everything we know today. This event, occurring around 13.8 billion years ago, gave birth to time, space, and matter. It was not an explosion in space, but rather an explosion of space, a concept that challenges our everyday understanding of reality. Quantum mechanics enters the narrative at the very first moments of the universe. Quantum fluctuations, tiny variations in energy at unimaginably small scales, are thought to have played a crucial role in the formation of the very first structures of the universe. These fluctuations, magnified by the rapid expansion of space, eventually formed the seeds for galaxies, stars, and ultimately, us. The inflation theory provides the mechanism for this rapid expansion. According to this theory, the universe underwent a brief period of extremely rapid expansion, faster than the speed of light, in the first fractions of a second after the Big Bang. This inflation stretched out these quantum fluctuations, smoothing out the universe to an almost uniform density, but also creating the structures we see today. Yet despite the explanatory power of these theories, there are still many unanswered questions. What caused the Big Bang? What was there before it? What is the nature of dark matter and dark energy, which together make up around 95% of the universe? Scientists are still grappling with these questions, using cutting-edge technology and innovative theories to probe the mysteries of our cosmic origins. So while we may not have all the answers yet, we're certainly on an exciting journey of cosmic discovery. The universe's origin story is still being written, and we can't wait to see what the next chapter reveals.